All right, so this lesson here is really mostly focused on understanding a type of notation that's probably new to you. It's called sigma notation. And then starts to apply it to some of the things we've seen before. But most of it is about understanding what this notation means. And here's an example of it right here. So sigma notation, also known as summation notation, is this. Everything you see here is an expression in sigma notation. And that big E looking thing, that's actually not the letter E, it's the letter sigma. It's a Greek letter, and that's why it's called sigma notation. But it represents a sum. It's also why it's called summation notation. And so let's look at what this means first. OK, so if I look at this here, actually I want to see the whole thing. I want to notice that all of this here is equivalent to all of this here. So how? And again, it probably looks really strange at first. I remember when I first would see this, it looked like Greek. Well, it is Greek. But it starts to make sense with just a little bit of practice. And so first, what this means here, this part right here, that represents the term that's being added repeatedly. But the term changes. And so how is a term changing? Well, the variable you see here is the same variable I see right there. And that is the part that's going to change from every term to the next. And literally what this means is I want to add the term an squared over and over again, starting where n equals 1 and stopping when n equals 5. That's what this means. And notice, if I look to the right of the equal sign, that n is first a 1, then a 2, then a 3, then a 4, and then a 5, and it stops there. Because there's a 5 at the top of the sigma notation. The a, which again, the important thing is it's not n. So it can be a number we know, it could be a variable. That just repeats every time. And same thing with the power of 2. Every single time it's n to the power of 2. So all that changes from one term to the next is the n. Now it doesn't have to be an n. It's whatever variable is right here. So if that's an x, then I'd probably have an x in all of these terms. Now notice, if you look at all of this, if we knew what a was, we could then add this all up. And so all of this here would equal a number. And if I asked you to evaluate this, I'd have to tell you what a is. And you would be able to add it all up. And then it would equal some value. OK, so let's now, with that quickly introduced, let's try using it for this. So what does this mean? Well, this means I want to add this term I, but there's nothing else going on. It's just I. So I starting at 1 and going all the way up to 100. So literally, this here means I want to add 1 plus.
Urine Song and Lily Chang to the office, please. Urine Song and Lily Chang to the office. All
right. So again, I start with 1 and then plus whatever comes after 1, 2, plus 3, plus, and so on, all the way up until I get to 100. So I'll write the last 3 terms. 98 plus 99 plus 100. And that's what this means. This statement right here means what you see right here. It means 1 plus 2 plus 3 plus 4 plus 5 all the way up to 100. So some conventions. Whatever variable, in this case it's an I, last time it was an n, whatever variable we're having right here, it can start at any number, but it has to be a whole number or an integer. So we don't have any decimals or fractions. The convention is we're always going up in 1 at a time. Other than that, it can be anything. So now let's actually evaluate this. And so I could literally add all these numbers together. Or this is an example of an arithmetic series. So you may remember this from grade 10. Honestly, I don't really care. One thing I'd like to point out, it's actually quite nice to add this up, and you've probably seen this before, that if I make pairs out of all of these, for example, 1 plus 100 is 101. If I add these two, 2 plus 99 is 101. 3 plus 98 is 101. And if I just keep going, 4 plus 97 is 101. So I can see, without actually literally adding this up, that I have all these pairs of 101. How many pairs do I have? Well, there's 100 terms here in pairs, so there must be 50 pairs. So that all this must equal 50 pairs of 101, and which is 50 times 101. Literally, it's 101 plus itself 50 times, which is 5,050. And so all of this here, when evaluated, equals 5,050. All of this here means this series right here. Now, this is not a geometric series. That's OK. It's a series. And all anytime you see summation notation, it's representing some sort of series. Maybe a geometric series, maybe not. OK, what if I have this? It's the sum from I equal 1 to 100 of 1. Just 1. So there's no I. It's not I, it's 1. So what does this mean? Well, this means 1 plus 1 plus 1 plus, and so on, 100 times. So that's literally what this means. This means 1 plus 1 plus 1, 100 times. So the 100 terms. So that's it. Pretty easy to know what this equals. 1 plus itself 100 times must equal 100. All right, what about this one here? What does this mean? Looking a bit more complex, but this time I have my variable I again. And there's the I right there. That's it. So this means I would start with, sounds silly to say, I would start with the start. And the start is 1. So I'm going to go to this term right here and write it down. But instead of having an I, I'm going to have a 1. So the first term here is going to be 2 times 1.1 to the power of 1 minus 1. That's the first term. OK, what's the second term? Plus. It's always a sum. 2 times 1.1 to the power of 2 minus 1. And so on until, so I'll go dot, 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 until we get to the last term. The last term is 100. So my last term will be 2 times 1.1 to the power of 100, take away 1. That's my last term. OK, that's what this means. So let's evaluate this. Well, first let me clean this up a bit. Each of my exponents, I'm subtracting 1 from it, so I might as well clean this up and say this here is the same as 2 times 1.1 to the power of 0. Well, 1.1 to the power of 0 is 1. Anything to the power of 0 is 1. So this here is 2 times 1. So just 2. Plus 2 times 1.1 to the power of 1. Plus, and so on, all the way to 2 times 1.1 to the power of 98. Sorry, 99. OK, so I've got to add this up. So what am I doing here? Well, first of all, notice this is a geometric series. And if it's not obvious yet that it's a geometric series, please realize as I go from one term to the next, so more announcements.
Mr. Lynn, please phone the office. Mr. Lynn, phone the office, please.
To realize the only difference is from one term to the next is we're multiplying by this 1.1 more and more times. 1.1 is the common ratio. And if that wasn't obvious yet, then, especially if you actually write out a few more terms and actually evaluate them, you get 2, you then get 2.2. And then each time it's the same as the previous term times 1.1. And there are 100 terms here. I know there's a power of 99 here, but this was like 2 times 1.1 to the power of 0. So there are 100 terms here. Plus, just so you look right here, if you're going from 1 to 100, it's pretty clear there's 100 terms. And so I want to add, what I can now tell is a geometric series. I want to find the sum of a geometric series with 100 terms, with a first term of 2, a common ratio of 1.1, and with 100 terms. So now I can, for the first time in this lesson, actually use what we saw in the last day. So I'm going to use this formula. And again, I know the common ratio. I know the number of terms I'm adding up is 100. I know my first term. All right. At this point, it's a matter of just calculations. And I should say actually over here S of 100, because we are finding 100 terms, the sum of that. And so all this equals about a big number I don't really care about too much as long as you get it on your calculator, 275,592. More announcements.
Unplaying to the office, please. Unplaying to the office.
This is what happens when I record a video at lunchtime. All right. So for the next scenarios, for each of these, I want to express what the answer would be as a series in sigma notation. But you don't actually have to figure it out. Now, that doesn't mean it's going to be easy. But for each of these, I'm trying to think, how can I connect this to a geometric series, which then I should be able to connect it to a sigma notation. Any geometric series can be written in sigma notation. And so let's look at this first scenario. A student jogs 5 kilometers on one day. Each day after that, she jogs 10% further. How many kilometers will she jog in total in 2 weeks? So let's first think about how this connects to a geometric series. So 5 kilometers is her first day. So 5. Plus, the next day, she jogs 1.1 times more. Now, why 1.1? Because multiplying by 1.1 is the same as adding 10%. And a little bit of grade 8 math right here. But adding 10% to a number is the same. Oh my God.
On Wang to the office, please. On Wang to the office.
I'm guessing he's left the school at lunch. Anyways, adding 10% to a number is the same as keeping your original number, all of it, plus an extra 10%. And 100% plus 10% is 110%. And how do you find 110% of a number? You multiply by 1.1 or 1.10. So adding 10% to a number is the same as multiplying by 1.1. Adding 10% to a number is the same as finding 110% of something. And that's why I got this 1.1 right here. And so 5 times 1.1 is 5.5. And I could do this again. So on the second day, she ran 5.5 kilometers. The next day after that, she keeps this up. We'll run about 6.05 kilometers, and so on, until I get to 2 weeks. So what is 2 weeks? 2 weeks is 14 days. So there should be 14 terms. Okay, so now I've got my geometric series kind of visualized. Okay, that's the first step. Now I need to express this in sigma notation. So let's start by making the Greek letter sigma. Okay, so first I need to think about what's happening from each term to the next. Well, I'm starting with a 5, and then I'm multiplying by 1.1 some number of times. The number of times I multiply by it depends on the term. So for example, the very first term, I'm not multiplying by 1.1 at all. So I want to, one way, if I pick the variable, I don't know, n, to be boring, then I could start by saying at n equals 0. So when n equals 0, my first term would be 5 times 1.1 to the power of 0. Literally, I'm not multiplying by 1.1. And then if I do that, I just got to think what goes up here. What's the last term? Well, it's 14, the last value of n, I should say. Well, there's 14 terms, but to get to that 14th term from 5, I'd have to multiply by 1.1 13 times. If you literally listed out the 14 terms, you would see there's 13 of these jumps. And so I could put a 13 right here. And notice the last term would be 5, the amount in the first day, times 1.1, adding 10%, 13 times, which makes sense because, again, after 14 days, you have increased 13 times. However, another way of doing this, it's actually a little more common, although this is totally correct, is to have almost the same thing. Everything here the same, times 1.1. But if you find it weird starting at 0, okay, let's start at 1, right? A geometric series, we usually talk about term 1. If we do that, then this would be 14. And the only difference is this would be n minus 1. If you write it like this, in some ways I like this better because this, especially this form we see right here, connects directly to the first lesson on geometric sequences. But in some ways I like this better because, I don't know, it's less stuff going on. It's all the same thing. Okay? This is a little bit more common just because it connects more directly to what we saw earlier. All right. So what about this question? An oil well produces 10,000 barrels of oil in a month when it first opened. Each month after that, it produces 15% less than the month before it. How much oil will the well have produced in 3 years? So first of all, let's make a sequence, or a series, I should say again. So start with 10,000. Plus, this time we're losing 15%. Losing 15% is the same as keeping 85%. Right? 100% minus 15% is 85%, which is the same as multiplying by 0.85. And so each time I go from one term to the next, I'm multiplying by 0.85. In this case, you get 8,500 plus, and so on. Okay, so that's the first hurdle done. Next, how many terms do I have here? I think of this as a geometric sequence. Well, in 3 years, that's going to be 36 months. So 36 months or 36 terms. Right, because every month it produces 15% less. So now I got my series figured out. So now let's create this in sigma notation. I'll do the same things before, 2 different ways. First, let's make this. So what's happening? Well, 10,000 is my first term. Let's write that down, 10,000. Times my common ratio, in this case, is 0.85. To the power of what? Well, it depends what I want to start with here. I'll go with n again. If I want to start with 0, because my first term is 10,000, not 8,500. My first term, I'm not multiplying by 0.85. If I want to start at 0, then I'll have just an n right here. And my last term would be 35. Because if you count from 0 to 35, you've counted 36 numbers. OK, and in some ways I like that. Really, or though, like before, just as good. And perhaps this may seem simpler, perhaps it seems more complex, is almost the same thing, where I have 10,000. 0.85, but if I want to start at 1, then I need to have n minus 1 here, because again, my first term is just 10,000, not 10,000 times 0.85, and then I go to 36. It makes those 36 terms more clear. All right, let's look at this, the last question before the final problem. So I have a fractal here, and let's look at the pattern of what's happening. No, I'm all good. And so I'm trying to see how many white triangles would there be in figure 10. Well, first, let's look at the pattern here. In figure 1, there's this one triangle. In figure 2, there's 1 plus 3 more. Yes, there's 4, but I want to see the pattern. So in figure 2, there's that one triangle plus 3 triangles more. In the third figure, there's the first triangle plus the 3 extra from the last figure plus 9 extras. Oh, I miscolored here. So what's the pattern that's happening here? Well, I can see the first term has 1 white triangle. The second term has 4, but more important is the second term has 1 plus 3 triangles, white triangles. The third figure, the third term, has 1 plus 3 plus 9. And so I can now see that the fourth term will have 1 plus 3 plus 9 plus 27. How do I know 27? Because I can see that each time I add more triangles, I'm adding 3 times more than before. So the next would be 1 plus 3 plus 9 plus 27, and so on. So in the 10th figure, well, that'd have to be, well, let's go straight to this. I mean, I can kind of see it would be 1 plus 3 plus 9 plus 27, a total of 10 times. And so I can say the sum of, I'm going to say n equals 1 to 10. There's 10 terms. OK, so I'm going to start with a 1. So how do I summarize this? Well, I could say my first term is 1 times 3, because that is really the common ratio each time. Each time I go to the next term, I'm adding 3 times more. So 1 times 3, how many times? Not n times. So if I have an n here, that implies my first figure has 3 triangles. Well, my first triangle has 1, so n minus 1. And really at this point, that 1 in the front we don't really need. So I could rewrite this a little bit simpler as saying that sigma n equals 1 to 10 of just 3 to the power of n minus 1. Or I could change this to a 0. I could change this to a 9, and I wouldn't have the minus 1 anymore. OK, but I keep talking about different ways of doing it. I'll just leave it like this. Which leads me to my final problem. OK, well, I have four expressions in sigma notation that I want to evaluate. All right. So with this, what does this mean? This means I want to add all the numbers from -10 to 10. That's really what this means. So this literally means here, -10 plus 1 larger than -10 is -9, plus -8, plus, and so on, all the way up to 10. So I'll say plus 8 plus 9 plus 10. That's what this means. So what does this equal? Well, notice if I pair these up, everything cancels out. 0, 0. So I think we can see the answer. This equals 0. That's a nice number. OK, let's look at the next one. Here I have same beginning and ending, but a different expression. It's 2 to the power of n. So this means I'm starting with, let me just change the color here. I'm starting with 2 to the power of negative 10 plus 2 to the power of negative 9 plus, and so on until I get all the way to 2 to the power of positive 10. That's what this means. OK, how many terms do I have here? If I count from negative 10 to positive 10, you may think there's 20 terms, but there's 21.
Will Katie Chang and Chloe Song come to the office, please? Katie Chang and Chloe Song to the office, please.
Because again, negative 10 to positive 10, there's 10 negative numbers, there's 10 positive numbers, and there's 0. There's 21 terms here. And so I'm adding 21 terms. Now this is a geometric sequence. How do I know? It's maybe a little more obvious if I show it as a fraction. For example, 2 to the negative 10 means 1 over 2 to the positive 10, which is 1 over 1,024. 2 to the negative 9 is 1 over 2 to the positive 9, remembering what negative exponents mean, which is 1 over, if you use your calculator, 512. And so on, all the way to 2 to the power of 10, which is just 1,024. So once I realize this, I realize I have a geometric series with 21 terms, a common ratio of 2 each time. Each time it's getting double the size, and 21 terms. And the first term is 1 over 1,024. And so now I can just go to this, and I can find the sum of 21 terms will equal my first term, 1 over 1,024, times 1 minus the common ratio, which is 2, to the power of the number of terms I'm adding up, which is 21 terms, all divided by 1 minus the common ratio again. And at this point, it's a matter of arithmetic. Use your calculator, and you get almost 2,047.999. I'm rounding it. Really, really close to 2,048. That said, I want to, for time reasons, I want to skip straight to, actually, you know what? I'm going to leave it there because this last, because I keep getting interrupted.
Chloe Song and Katie Chang to the office, please. Chloe Song and Katie Chang to the office, please. So,
If I keep talking, I'll probably just keep getting more interruptions, which is probably the most entertaining part of this video. But these last two examples here, great questions. Notice the very last one has infinity in the top. That said, they're actually very similar to what we just did, but I want to leave it for now, because again, well, I'm tired of getting interrupted, and I'm hoping we'll have a chance at some point to look at these in class. But at this point, I'm going to stop here. Remember, most of this is really about understanding how to read sigma notation. And again, if you have a geometric series, it can always be written in sigma notation. But don't assume all sigma notation applies to a geometric series. All right, and we've seen that today. Some of the examples are not geometric series. For example, this example right here, that's not a geometric series. So it's definitely not every sigma notation has to be a geometric series, but a lot will, because that's the focus of what we're looking at right now. All right, I'm going to stop this before there's another call for